Chapter 4, Carbon and its Compounds. Introduction to Organic Chemistry.
Carbon is one of the most widely distributed elements. It is present in
living things like plants, animals, and human beings.
It is interesting to know that carbon is present in food items such as sugar, cereals, pulses, etc. It is also present in paper, plastic, wood, petrol, and many other things. Carbon is present in nature both in the free state and in the combined state. It is found in the free state as graphite and diamond. In air, it occurs in combination with oxygen as carbon dioxide. Although carbon dioxide is only 0.03% by volume in air, it plays an important role in the food cycle through the process of photosynthesis. Carbon is also found in fuels like biogas, petroleum, marsh gas, and coal.
Carbon compounds are so widely distributed that the study of carbon and its compounds forms a separate stream in chemistry called organic chemistry. Thus, the compounds containing carbon are called organic compounds. Apart from carbon, most of the organic compounds contain hydrogen, oxygen, and other elements. Earlier, it was believed that a vital force present in living organisms could produce organic compounds. This came to be known as the vital force theory. As a result, no attempts were made to synthesize organic compounds in the laboratory till Friedrich Wöhler in 1828 synthesized urea, an organic compound, from ammonium cyanate in the laboratory. This experiment disproved the vital force theory. Since then, many organic compounds have been discovered naturally as well as synthesized artificially. The covalent bond. Bonds formed by sharing of electrons are known as covalent bonds. The atomic number of carbon is 6. And its electronic configuration is 2, 4. A carbon atom has 2 electrons in the first orbit and 4 electrons in the outermost orbit. It can gain or lose 4 electrons to attain the configuration of the nearest noble gas. If it were to gain 4 electrons to form C4- anion, it would be difficult for the 6 protons in its nucleus to hold on to the 10 electrons. Similarly, if in order to lose 4 electrons to give C4+ cation, it would require a large amount of energy. These problems are overcome by sharing of electrons to form covalent bonds. Let us understand this with the help of a few examples. Oxygen and nitrogen are also covalent molecules. How is an oxygen molecule formed? An oxygen molecule is formed by the combination of 2 oxygen atoms. The atomic number of oxygen is 8. The electronic configuration is 2, 6. An oxygen atom requires 2 electrons to complete its octet. If 2 oxygen atoms are brought closer, 2 electrons from each oxygen atom are shared between the 2 oxygen atoms. Thus, the octet of both the oxygen atoms is completed. As there are 2 pairs of electrons that are shared between them, the covalent bond formed is a double bond. Oxygen molecule is represented as O double bond O. Oxygen molecule can also be represented by an electron dot and cross structure. How is a nitrogen molecule formed? Nitrogen molecule is formed by the combination of two nitrogen atoms. The atomic number of nitrogen atom is 7 and its electronic configuration is 2, 5. A nitrogen atom requires 3 electrons to complete its octet. If 2 nitrogen atoms are brought closer, 3 electrons from each nitrogen atom are shared between the 2 nitrogen atoms. Thus, the octet of both nitrogen atoms is completed. As there are 3 pairs of electrons that are shared between the nitrogen atoms, the bond formed is a triple bond. Nitrogen molecule so formed is represented as N triple bond N. A nitrogen molecule can also be represented by an electron dot and cross structure. Methane is known as marsh gas as it is produced naturally by the decomposition of vegetable matter in marshy lands. Methane is used as domestic and industrial fuel. How is a methane molecule formed? A methane molecule contains 1 carbon atom and 4 hydrogen atoms. The atomic number of carbon is 6 and its electronic configuration is 2, 4. A carbon atom has 2 electrons in the first orbit and 4 electrons in the outermost orbit. Carbon requires 4 electrons to attain the nearest inert gas configuration, that is, of neon. Hence, carbon is tetravalent. The atomic number of hydrogen atom is 1. Hydrogen atom has 1 electron in its outermost orbit. It requires only 1 electron to attain the inert gas configuration of helium. If 4 such hydrogen atoms share their lone electron with a carbon atom, then each of the 4 hydrogen atoms can complete their duplet state and the carbon atom can also complete its octet state. In this way, 1 carbon atom and 4 hydrogen atoms combine to form a methane molecule. The molecular formula of methane is CH4. Since only a single pair of electrons is shared between the carbon and each hydrogen atom, a methane molecule thus formed has 4 carbon-hydrogen single bonds. Methane can also be represented by an electron dot and cross structure. In the methane molecule, the carbon atom is centrally placed. Electrons of carbon are shown as crosses and the electrons of hydrogen are shown as dots. Organic compounds are covalent compounds having low melting and boiling points. This is because the bonds between 2 or more molecules of a covalent compound are weak. Hence, a small amount of energy is required to weaken the forces of attraction between them. Let us study the melting points and boiling points of some compounds of carbon. The melting point of acetic acid is 290 Kelvin. Chloroform is 209 Kelvin and ethanol is 156 Kelvin. Methane has a melting point of 90 Kelvin. The boiling point of acetic acid is 391 Kelvin. Chloroform is 334 Kelvin and ethanol is 351 Kelvin. The boiling point of methane is 111 Kelvin. Occurrence of carbon. The element carbon occurs in the free state as diamond and graphite. It also occurs in the combined state as carbon dioxide, methane, carbonates like chalk, limestone, etc., fossil fuels like coal, petroleum, and natural gas. Carbon is also present in organic compounds like carbohydrates, proteins, fats, etc. . Diamond and graphite are allotropes of carbon. What are allotropes of an element? Allotropes of an element have different physical forms but the same chemical properties. How are diamond and graphite different from each other? The diamond is a hard, beautiful crystalline substance, while graphite is a soft, grayish-black crystalline substance. Each carbon atom in diamond is linked to 4 other carbon atoms held at the corners of a regular tetrahedron by strong covalent bonds. A diamond crystal is made up of carbon atoms which are strongly bonded to each other by a network of covalent bonds. These strong covalent bonds extend in all directions through the entire crystal. This gives the diamond a rigid, 3-dimensional structure. On the other hand, each carbon atom in graphite is covalently bonded to 3 other atoms of carbon, forming layers of linked hexagons. These layers are held by weak forces and can slide over one another, making it a comparatively soft substance. Do diamond and graphite conduct electricity? Let us perform a small experiment to know this. Arrange a circuit using connecting wires, a bulb, a battery, a switch and crocodile clips. Insert a piece of diamond between the ends of the crocodile clips. Switch on the current. Does the bulb glow? No, it does not. Now place a piece of graphite between the ends of the crocodile clips. Switch on the current. Now does the bulb glow? Yes, it does. Why does this happen? In diamond, all the 4 valence electrons of each carbon atom are used in the formation of bonds. Hence, there are no free electrons. Diamond is therefore a non-conductor of electricity. In graphite, 3 valence electrons of each carbon atom are used in bond formation and the 4th valence electron of each carbon atom is free to move. The presence of free electrons makes graphite a good conductor of electricity. How are the chemical properties of both diamond and graphite the same? Both diamond and graphite on burning in oxygen form carbon dioxide. Therefore, we can say that both diamond and graphite show the same chemical properties. Diamond is used for making jewelry. Black diamonds are used in cutting instruments like glass cutters. Graphite is used as a lubricant in machinery. It is also used in making electrodes in dry cells and for making the cores of pencils called pencil leads.
Fullerene. Fullerene is a recently discovered allotrope of carbon. It is also known as C60 or buckyball. It forms discrete particles. The carbon atoms in fullerene are joined to each other in pentagonal and hexagonal structures. As a result, the structure of fullerene resembles a football. It is interesting to know that fullerene was named after the architect Richard Buckminster Fuller for the kind of domes he had built. Harold Kroto, Robert Curl, and Richard Smalley were awarded the Nobel Prize for Chemistry in 1996 for the C60 form of carbon. It is expected that C60 could be used in the revolutionary research related to superconductivity. Properties of fullerene are still being studied.
The versatility of carbon. Have you ever wondered why carbon atoms can form so many organic compounds? This is because of the unique properties exhibited by carbon. Let us see some of them. Catenation. The most unique property exhibited by carbon is its ability to combine with itself. This property is called as catenation. Catenation means self-linking. Due to this property, carbon can form long chains which gives rise to a large number of carbon compounds or organic compounds. A long chain of carbon atoms can act as a backbone to which other atoms can attach in a number of ways to form many carbon compounds. In addition to long chains, they can form branched and ring structures. Carbon atoms can also be linked by double and triple bonds. Compounds consisting of only single bonds are called saturated compounds, while those consisting of multiple bonds are called unsaturated compounds. There are many other elements which have the ability to form long-chained compounds. Silicon is another element which exhibits catenation. Silicon forms compounds with hydrogen which have chains of up to 8 atoms. But these compounds are unstable and reactive. On the other hand, the carbon-carbon linkage is stable, and hence we see a large number of long-chained carbon compounds. Tetravalency. The valency of carbon is 4. That is, it is tetravalent. This makes carbon capable of forming bonds with 4 other monovalent atoms. The bonding atoms may be carbon atoms or atoms like hydrogen, oxygen, nitrogen, sulfur, phosphorus, chlorine, and many more atoms. This results in the formation of a wide range of compounds. The reason for the formation of a wide range of compounds is also the small size of carbon atom. Due to the small size, the nucleus can hold the shared pair of electrons more strongly. Thus, the bonds formed are exceptionally strong and the compounds formed are stable. Chemistry of carbon compounds. Saturated and unsaturated hydrocarbons. Compounds made up of hydrogen and carbon only are called hydrocarbons. Hydrocarbons in which the carbon atoms are linked to each other only by single bonds are called saturated hydrocarbons. Saturated hydrocarbons are also called alkanes. The general molecular formula for an alkane is CnH2n plus 2, where N is the number of carbon atoms. If an alkane has one carbon atom in its molecule, then the value of N is 1 and its molecular formula is CH4. This is the molecular formula for methane. If an alkane has 2 carbon atoms in its molecule, then the value of N is 2 and its molecular formula is C2H6. This is the molecular formula for ethane. Since only a single pair of electrons is shared between the carbon and hydrogen atoms, alkanes consist of carbon-hydrogen single bonds. Hydrocarbons in which the carbon atoms are linked to each other by double or triple bonds are called as unsaturated hydrocarbons. Hydrocarbons with carbon-carbon double bonds are called alkenes. The general molecular formula for an alkene is CnH2n. If an alkene has 2 carbon atoms in its molecule, then the value of N is 2 and its molecular formula is C2H4, which is ethene. 2 hydrogen atoms are bonded to each carbon atom. The valencies of each of the carbon atoms is satisfied only if there is a double bond between the carbon atoms. Hence, ethene is written as CH2 double bond CH2. If an alkene has 3 carbon atoms in its molecule, then the value of N is 3 and its molecular formula is C3H6, which is the molecular formula for the hydrocarbon propene. Propene is written as CH3 single bond CH double bond CH2. Propene can also be written as CH2 double bond CH single bond CH3. Hydrocarbons with carbon-carbon triple bonds are called alkynes. The general formula for an alkyne is CnH2n-2. If an alkyne has 2 carbon atoms in its molecule, then the value of N is 2 and its molecular formula is C2H2. This is the molecular formula for ethyne. Ethyne is written as HC triple bond CH. If an alkyne has 3 carbon atoms in its molecule, then the value of N is 3 and its molecular formula is C3H4, which is the molecular formula for propyne. Propyne is written as CH3 single bond C triple bond C single bond H. Propyne can also be written as H single bond C triple bond C single bond CH3. Chains, branches and rings. Straight chains. The general formula of alkanes is CnH2n plus 2, where N is the number of carbon atoms. If we know the value of N, that is the number of carbon atoms, then we can determine the molecular formula and the structural formula of the alkane. Methane is the simplest hydrocarbon. It is a saturated hydrocarbon and an alkane. If we increase the number of carbon atoms by 1 and the number of hydrogen atoms by 2, then we get the compound C2H6. This is ethane, which is the next member of the family of alkanes. If we add 1 more carbon atom and 2 hydrogen atoms to ethane, we get the compound propane with the formula C3H8. Let us determine the formulae and structures of some saturated hydrocarbons and complete the table. If N is equal to 1, the number of carbon atoms is also 1. The compound is methane, and the formula of the compound will be C1H2 multiplied by 1 plus 2. This gives the molecular formula CH4. The structural formula will have 1 carbon bonded with 4 hydrogen atoms. If N is equal to 2, the number of carbon atoms is also 2. The organic compound is ethane, and the formula will be C2H2 multiplied by 2 plus 2. This gives the molecular formula C2H6. The structural formula will have 2 carbon atoms bonded with 6 hydrogen atoms. If N is equal to 3, the number of carbon atoms is also 3. The organic compound is propane, and the formula will be C3H2 multiplied by 3 plus 2. This gives the molecular formula C3H8. The structural formula will have 3 carbon atoms bonded with 8 hydrogen atoms. If N is equal to 4, the number of carbon atoms is also 4. The organic compound is butane, and the formula will be C4H2 multiplied by 4 plus 2. This gives the molecular formula C4H10. The structural formula will have 4 carbon atoms bonded with 10 hydrogen atoms. If N is equal to 5, the number of carbon atoms is also 5. The organic compound is pentane, and the formula will be C5H2 multiplied by 5 plus 2. This gives the molecular formula C5H12. The structural formula will have 5 carbon atoms bonded with 12 hydrogen atoms. If N is equal to 6, the number of carbon atoms is also 6. The organic compound is hexane, and the formula will be C6H2 multiplied by 6 plus 2. This gives the molecular formula C6H14. The structural formula will have 6 carbon atoms bonded with 14 hydrogen atoms. If N equals to 7, the number of carbon atoms is also 7. The organic compound is heptane, and the formula will be C7H2 multiplied by 7 plus 2. This gives the molecular formula C7H16. The structural formula will have 7 carbon atoms bonded with 16 hydrogen atoms. In all the examples which we have seen, the carbon atoms are in the form of a continuous chain. Such compounds are called straight chain compounds. Let us see the electron dot and cross structures of the alkanes propane and hexane. Electrons of carbon are shown as crosses, and the electrons of hydrogen are shown as dots. Branched alkanes. Alkanes can also be in the form of branched chain structures. Take the example of pentane. The molecular formula of pentane is C5H12. Pentane can have 3 structures. The first structure has 5 carbon atoms in the form of a straight chain. The second structure has 4 carbon atoms in a chain, and the fifth is in the side chain. The third structure has 3 carbon atoms in a chain and 2 in the side chain. Hence, we will get a straight chain structure and branched chain structures of pentane. Such compounds which show identical molecular formula but different structures are called isomers, and the property is called isomerism. Rings. There are some hydrocarbon molecules in which carbon atoms are joined to form a closed ring. One such example is cyclohexane. The carbon skeleton of a cyclohexane molecule contains 6 carbon atoms arranged in the form of a hexagonal ring. The molecular formula of cyclohexane is C6H12. If 2 hydrogen atoms are attached to each of the carbon atoms, we get the complete molecule of cyclohexane. You must have observed that all the carbon atoms in cyclohexane are bonded to each other by single bonds. This is a saturated hydrocarbon. Let us consider the example of benzene. The molecular formula of benzene is C6H6. A benzene molecule consists of 6 carbon atoms forming a hexagonal ring. There are alternate single and double bonds in the structure. This is an unsaturated hydrocarbon. Let us see the electron dot and cross structures of cyclohexane and benzene. Electrons of carbon are shown as crosses, and the electrons of hydrogen are shown as dots. Nomenclature. Organic compounds are named according to the IUPAC system. That is, the International Union of Pure and Applied Chemistry system. The IUPAC system considers all organic compounds as the derivatives of alkanes. The name of the compound can be expressed from the root of the basic organic compound, the prefix and the suffix. Let us understand each of these terms. The root of the organic compound indicates the nature and the number of carbon atoms in the basic carbon skeleton. The root word is modified according to the longest carbon chain. For example, if the chain has only one carbon atom, the root is methane and the root word is meth. A chain with 2 carbon atoms has the root word eth. A chain with 3 carbon atoms has the root word prop. A chain with 4 carbon atoms has the root word but. A chain with 5 carbon atoms has the root word pent. A chain with 6 carbon atoms has the root word hex. A chain with 7 carbon atoms has the root word hept. A chain with 8 carbon atoms has the root word oct. The suffix denotes the type of bonds or functional group present in the carbon chain. The suffix added to the root word indicates the saturation or unsaturation in the carbon chain. For example, if the carbon chain is saturated, the suffix is ane for the generic name alkane. If the carbon chain is unsaturated, having a double bond, then the suffix is ene for the generic name alkene, and if the carbon chain is unsaturated, having a triple bond, the suffix is yne for the generic name alkyne. The number of bonds present between any 2 adjacent carbon atoms in alkenes is 2. The number of bonds present between any 2 adjacent carbon atoms in alkynes is 3. Next is the prefix. The prefix denotes the presence of other functional groups and their position. Let us name a few compounds using the root, prefix and suffix terminology. Take the example of C2H5OH. From the structural formula, we can say that one hydrogen atom is substituted by the OH group. Functional group is alcohol. First, select the longest chain of carbon atoms. In this compound, the longest chain is of 2 carbon atoms. Therefore, the parent alkane is ethane. Since the functional group is alcohol, remove the E from the word ethane and substitute it with OL. The carbon atom to which the OH group is attached is the first carbon atom, hence it is numbered as C1. The other atoms are numbered accordingly. Thus, the compound C2H5OH is named as ethane 1-ol, which indicates that the functional group OH is attached to the carbon atom at the end of the chain or the first carbon atom. In the IUPAC system, alcohols are also named as alkanols. Let us consider some more examples. Consider the given molecule. In this structure, one hydrogen atom is substituted by the Br group. The functional group is a halide, that is, a bromo group. Select the longest chain of carbon atoms. In this compound, the longest chain is of 3 carbon atoms and it is in a straight chain. Therefore, the parent alkane is propane. The carbon atom nearest to the substituted carbon is numbered as C1. Since the bromo group is attached to the second carbon atom, the compound is called 2-bromopropane. Consider the given compound. In this compound, the longest chain is of 4 carbon atoms and it is a straight chain. Therefore, the parent alkane is butane, but for unsaturated hydrocarbons, the suffix ene is added. So this chain is named as butene. Since the numbering of carbon atoms starts from the carbon atom nearest to the double bond, The carbon atom on the extreme right is numbered 1. If the position of the double bond is between the C1 atom and the C2 atom, then the lower number of carbon atom will be used as the prefix to indicate the position of the double bond. In this case, the compound is known as but1-ene. What is the IUPAC name of this compound? In this compound, the longest chain is of 4 carbon atoms and it is in a straight chain. Therefore, the parent alkane is butane. Since it is an unsaturated hydrocarbon, the above chain is named as butene. Here, the double bond is between the C2 atom and the C3 atom. Therefore, the compound is known as but2-ene. How is an unsaturated compound containing a triple bond named? Consider the given compound. In this compound, since there are 2 carbon atoms, the parent compound is ethane. There is a triple bond between the 2 carbon atoms, so the suffix used is YNE. So the compound is named as ethyne. How will you name an aldehyde, a ketone, and a carboxylic acid? Consider this example: CH3, CH2, CHO. From the structural formula, we can say that one hydrogen atom is substituted by the CHO group. The functional group is aldehyde. In this compound, the longest chain is of the 3 carbon atoms. Therefore, the parent alkane is propane. In the IUPAC system, the suffix used for an aldehyde is -al. Now, remove the E from the word propane and substitute it with -al. Thus, the compound CH3, CH2, CHO is named as propanal. Generally, the CHO group is attached at the end of the carbon chain. Similarly, consider a ketone CH3COCH3. In this compound, the longest chain is of 3 carbon atoms. Therefore, the parent alkane is propane. In the IUPAC system, the suffix used for a ketone is -on. Now, remove the E from the word propane and substitute it with -on. Thus, the compound CH3COCH3 is named propanone. Let us study some more examples. CH3CH2CH2OH. In this compound, the longest chain of carbon atoms contains 3 carbon atoms. Therefore, the parent alkane is propane. The functional group is alcohol and the OH group is attached to the C1 carbon atom. Therefore, the compound is named as propane-1-ol. HCOOH. Since there is only 1 carbon atom, the parent alkane is methane. The functional group here is an acid. Therefore, the suffix used is oic acid. The compound is therefore named as methanoic acid. Chemical properties of carbon compounds. Combustion. Most of the allotropic forms of carbon burn in oxygen to give carbon dioxide along with a large amount of heat or light or both. When methane burns in air, it produces carbon dioxide, water and a large amount of heat and light. They are exothermic reactions. That is why natural gas, which contains methane as a major constituent, is used as a fuel in homes and industry. Similarly, butane also burns in air to produce carbon dioxide, water and a large amount of heat and light. About 2,658 kilojoules of heat is produced in the reaction. All hydrocarbons burn in air or oxygen to form carbon dioxide and water. This process of burning is called combustion. Saturated hydrocarbons, that is alkanes, generally burn in a sufficient supply of air, producing a clean blue flame, that is, an oxidizing flame. Even in homes, when gas stoves or kerosene stoves are used, a sufficient supply of air is used as to get a clean blue flame. In a limited supply of air, alkanes like methane undergo an incomplete combustion to produce carbon black. Unsaturated hydrocarbons burn in air with a yellow flame, producing lots of smoke. This is because the percentage of carbon in unsaturated hydrocarbons is comparatively higher than in alkanes, which does not get oxidized completely in the oxygen of the air. The air contains only about 21% of oxygen in it, which is not sufficient for the complete combustion of unsaturated hydrocarbons. If an unsaturated hydrocarbon is burnt in pure oxygen, then it will burn completely, producing a blue flame. Let us understand this more clearly with an example. If a mixture of acetylene is burnt in oxygen, acetylene burns completely, producing a blue flame. This is called the oxyacetylene flame. The oxyacetylene flame produces a very high temperature, which is used for welding metals. A mixture of acetylene and air cannot be used for welding because burning of acetylene in air produces a sooty flame due to incomplete combustion, which is not enough for welding of metals. Let us perform the following activity to understand complete combustion and incomplete combustion of carbon compounds. We shall be using a Bunsen burner for this activity. First, keep the air holes of the Bunsen burner fully open and light the burner. We see that when the air holes are fully open, the butane gas present in the burner burns with a blue flame or a non-sooty flame. In this case, the saturated hydrocarbon butane undergoes complete combustion. The color of the flame is blue. Now, make the air holes smaller and smaller to reduce the amount of air going into the burner. As we go on reducing the amount of air going into the burner, the butane gas present in the burner starts burning with a sooty flame. When the air hole is completely closed, the gas burns with a highly sooty flame, producing a thick black smoke. In this case, the saturated hydrocarbon butane undergoes incomplete combustion. The color of the flame is yellow. Now, let us understand why some substances burn with a flame and some do not burn with a flame. We know that a candle, cooking gas and kerosene oil burn with a flame. Gaseous fuels like cooking gas burn with a flame. Solid or liquid fuels which vaporize on heating to form a gas burn with a flame. Do coal or wood also burn with a flame? No, they do not. Coal and wood only produce a red glow when burnt. Why does this happen? This happens because coal and wood contain some volatile substances which vaporize and burn with a flame in the beginning. When all the volatile substances present in coal and wood get burnt, then the remaining coal or wood only produces a red glow and gives heat without producing any flame. How were coal and petroleum formed?
Coal was formed some 200 to 300 million years ago from the remains of plants such as ferns, mosses, and trees which existed in swampy forests. As plants and trees died, their remains sank to the bottom of swampy areas. These dead plants and trees got covered with a layer of mud, water, rocks and soil by accumulating layer upon layer over a period of time. As more and more matter piled up, the bottom layers got compressed. Consequently, sandstone and other sedimentary rocks were formed. Heat and pressure converted the dead plants first into a spongy brown material called peat, then into a brown hard substance called lignite, and finally into coal. Increasing heat and pressure from the top layers along with bacterial action gradually changed the material into coal. With the formation of each successive layer of coal, the amount of carbon present in the deposit increased and the level of impurities decreased. Petroleum was formed from the dead remains of living organisms in the sea that were once trapped inside the sedimentary rocks millions of years ago. These remains settled down at the bottom of the seas and oceans in the form of sediments. Over millions of years, they were covered with several layers of sand and clay. Absence of air, intense heat and pressure converted these remains into petroleum and natural gas.
Oxidation. Carbon compounds undergo oxidation to give carbon dioxide. In addition to this, oxidation of carbon compounds using oxidizing agents give other carbon compounds. Let us understand this with the help of an activity. Take about 3 ml of ethanol in a test tube and warm it gently in a water bath. Now add a few drops of a solution of alkaline potassium permanganate. Initially, the purple color of potassium permanganate disappears, but as we add excess of alkaline potassium permanganate, the purple color persists. Alkaline potassium permanganate, being a strong oxidizing agent, provides nascent oxygen for oxidizing substances. In this reaction, ethanol gets oxidized to form ethanoic acid. Once ethanol is oxidized, the excess potassium permanganate gives a purple color to the solution. Reagents which provide nascent oxygen are called oxidizing agents. Acidified potassium dichromate can also act as an oxidizing agent and can oxidize alcohols to acids. Addition reaction. Unsaturated hydrocarbons like ethane combine with hydrogen in the presence of catalyst nickel to form ethane. Let us see the reaction between ethene and hydrogen. Ethene reacts with hydrogen in the presence of a catalyst nickel to form ethane. One hydrogen atom adds to each carbon atom of ethene, due to which the double bond opens up to form ethane. We can say that addition reactions convert an unsaturated compound to a saturated compound. Consider another example. Ethene reacts with bromine to form 1,2-dibromoethane. One bromine atom adds to each carbon atom of ethene, due to which the double bond opens up to form a compound 1,2-dibromoethane with a single bond. Alkynes, for example, ethyne, react with bromine first to form 1,2-dibromoethene. It again reacts with bromine and then finally forms 1122 tetrabromoethane. This is an addition reaction. Such reactions in which two molecules react to form a single product are known as addition reactions. These reactions take place only in unsaturated compounds containing double or triple bonds. Thus, only alkenes and alkynes give addition reactions because alkenes contain double bonds and alkynes contain triple bonds. Substitution reaction. What is the reaction between methane and chlorine? Methane reacts with chlorine to form methyl chloride and hydrogen chloride. In this reaction, one hydrogen atom is substituted by a chlorine atom, converting methane to methyl chloride. Reactions in which one or more hydrogen atoms of a hydrocarbon are replaced or substituted by some atoms are called substitution reactions. Similarly, an alkyl halide like ethyl halide reacts with potassium hydroxide to form ethyl alcohol and potassium iodide. In this reaction, the iodine atom is substituted by the hydroxyl group. Substitution reactions like chlorination are a characteristic property of saturated hydrocarbons or alkanes. Unsaturated hydrocarbons do not give substitution reactions with halogens, they give addition reactions. Some important carbon compounds. Almost all organic compounds are invaluable to us. Let us understand the importance of two such compounds. Ethanol. The common name for ethanol is ethyl alcohol or spirit. Ethanol is the second member of the homologous series of alcohols. The first member of the series is methyl alcohol. The formula of ethanol is C2H5OH. It is a straight chain compound and has a linear structure. Let us discuss the physical properties of ethanol. Ethanol is a colorless liquid with a pleasant odor. It has a low boiling point of 78 degrees Celsius and freezing point of minus 114 degrees Celsius. Ethanol is combustible and burns with a blue flame to form carbon dioxide and water. Let us discuss some reactions of ethyl alcohol. Reaction of sodium metal. Ethyl alcohol reacts with sodium metal to form sodium ethoxide and hydrogen gas. This is also a test for alcohols. The evolution of effervescence of hydrogen gas indicates that the given organic compound is an alcohol. Reaction with phosphorus trichloride. Ethyl alcohol reacts with phosphorus trichloride to form ethyl chloride and phosphorus acid. Dehydration of ethanol. When ethanol is heated with an excess of sulfuric acid at 444 Kelvin, it gets dehydrated to form ethene. Sulfuric acid acts as a dehydrating agent and removes a water molecule from ethanol. In this reaction, the hydrogen atom from the CH3 group and the OH group from the CH2OH group are removed to form water. This results in the formation of ethene, an unsaturated hydrocarbon. Uses of ethanol. Ethanol is used as an antiseptic to sterilize wounds and syringes in hospitals. Ethanol, being a good solvent, is used in medicines such as tincture iodine, cough syrups, and tonics. It is also used in the preparation of alcoholic drinks. Ethanol is also used as a fuel in cars along with petrol, since it is a cleaner fuel and produces only carbon dioxide and water when burnt in sufficient amounts of air. Let us discuss the harmful effects of alcohol. If large quantities of alcohol are consumed, it slows down the activity of the central nervous system, due to which the judgment of the person is impaired and the reactions of the person become slow. Methanol, even if consumed in small quantities, can cause death of the person. Methanol gets oxidized in the liver to form methanal. Methanal reacts with the cells of the body, causing coagulation of the protoplasm. Due to this, the cells stop functioning normally, resulting in the death of the person. Methanol also affects the optic nerve, causing blindness. Ethanoic acid. Common name for ethanoic acid is acetic acid. Ethanoic acid is the second member of the homologous series of carboxylic acids. The first member of the series is methanoic acid. The formula of ethanoic acid is C2H4O2 or CH3COOH. It is a straight-chain compound and has a linear structure. Let us discuss the physical properties of ethanoic acid. Ethanoic acid is a colorless corrosive liquid with a pungent odor. Ethanoic acid, when dissolved in water, produces less hydrogen ions, hence it is a weak acid. At ordinary temperature, ethanoic acid is in the liquid state. When ethanoic acid is cooled below 290 Kelvin, it solidifies into an ice-like mass which looks like a glacier. Therefore, ethanoic acid is also called as glacial acetic acid or simply acetic acid. Let us perform an activity to compare the strength of ethanoic acid, a carboxylic acid, and dilute hydrochloric acid, a mineral acid. Take some dilute ethanoic acid and dilute hydrochloric acid in separate test tubes. Dip a blue litmus paper in each test tube. What do you observe? Both dilute ethanoic acid and dilute hydrochloric acid turn blue litmus paper red. This shows that both ethanoic acid and hydrochloric acid are acidic in nature, but the litmus test does not prove that ethanoic acid is a weak acid. Now, let us test both these acids using a universal indicator paper. Dip a universal indicator paper in both the acids. What do you observe? Dilute ethanoic acid turns the universal indicator paper orange, shows that the pH is about 4. Dilute hydrochloric acid turns the universal indicator paper to red, showing that its pH is about 1. This indicates that ethanoic acid is a weak acid. Hydrochloric acid is a strong acid. Carboxylic acids like ethanoic acid are only partially ionized in the solution to give a small number of hydrogen ions. They are therefore weak acids. Mineral acids like hydrochloric acid are completely ionized in the solution to give a large number of hydrogen ions. Therefore, they are strong acids. Reactions with chlorine. Acetic acid reacts with chlorine to form monochloroacetic acid and hydrogen chloride. Here, one hydrogen atom from the methyl group of acetic acid is replaced by one chlorine atom. Monochloroacetic acid further reacts with chlorine to form dichloroacetic acid. Here, one more hydrogen atom is replaced by the chlorine atom. Dichloroacetic acid further reacts with chlorine to form trichloroacetic acid. Here, the third hydrogen atom near the carbon atom is replaced by the chlorine atom. In this way, all the hydrogen atoms are replaced by the chlorine atoms. Reactions with sodium metal or zinc metal. Acetic acid reacts with sodium metal to form sodium acetate and hydrogen gas. Similarly, acetic acid reacts with zinc metal to form zinc acetate and hydrogen gas. Esterification. Acetic acid reacts with ethyl alcohol in the presence of anhydrous zinc chloride or sulfuric acid to form ethyl acetate and water. Ethyl acetate is an ester. This process is called esterification. This is also a test for carboxylic acids. The formation of an ester shows that the organic compound is carboxylic acid. Esters are sweet-smelling volatile liquids. They are used in making perfumes. They are also used in making artificial flavors and essences used in ice creams, sweets, etc. Hydrolysis of esters. When an ester is heated with sodium hydroxide solution, it gets hydrolyzed to form alcohol and sodium salt of the carboxylic acid. This process is called saponification, which is used in the manufacture of soaps. When ethyl acetate is boiled with sodium hydroxide solution, sodium ethanoate and ethanol are produced. Reactions with carbonates and bicarbonates. Let us perform an activity to understand the reaction between ethanoic acid and sodium carbonate. Take some sodium carbonate in a test tube and add about 2 ml of ethanoic acid. What do you observe? There is brisk evolution of a gas. Now, fix a bent tube and allow the gas to react with lime water. The lime water turns milky. This shows that the gas evolved was carbon dioxide. Let us see the reaction. Ethanoic acid reacts with sodium carbonate to form sodium ethanoate, carbon dioxide, and water. Similarly, ethanoic acid reacts with sodium bicarbonate to form sodium ethanoate, carbon dioxide, and water. Reaction with sodium hydroxide. Ethanoic acid reacts with a base like sodium hydroxide to form a salt sodium ethanoate and water. In this reaction, ethanoic acid behaves like a mineral acid and reacts with a base to form salt and water. Soaps and detergents. When fats or oils are heated with either sodium hydroxide or potassium hydroxide, they form the respective sodium or potassium salt of the fatty acid along with glycerol. This salt so formed is called as soap, and the process is called saponification. Let us understand the structure of a soap molecule. The soap molecule has a tadpole-shaped structure. At one end of the soap molecule is a long hydrocarbon chain, which is hydrophobic or water-repelling in nature. This end is insoluble in water but soluble in oil or grease. At the other end of the soap molecule is the short ionic part of sodium carboxylate. This end is water-attracting or hydrophilic in nature and hence soluble in water but insoluble in oil or grease. When soap is mixed with water, the soap molecules form lather or they foam. The soap molecules cluster together to form spherical micelles called as soap micelles. When a dirty cloth is dipped in water containing soap, the soap particles and dirt come in contact with each other. The non-polar hydrocarbon ends of the soap molecule surround the oil or grease particles and begin to dissolve them. The polar carboxylate ions remain directed towards water. Thus, each oil or grease particle gets surrounded by a number of negatively charged hydrocarbon ends. The soap micelles trap the dirt particles which are attracted to the dirty cloth. Since like charges repel each other, the oil or grease drop breaks off and forms smaller grease droplets and gets dispersed in water. In this way, the oil or grease particles from the dirty cloth are removed, making the cloth clean. The purpose of using soap is to make oily or greasy particles mix with water so that they can be washed away during agitating and rinsing. Let us perform an activity to understand this. Take about 10 ml of water in 2 test tubes labeled A and B. Add a few drops of oil to each of the test tubes. Now, add a few drops of soap solution to test tube B. Cork both the test tubes and shake them vigorously. What do you observe? In test tube A, the layer of oil floats above the layer of water. In test tube B, oil mixes with water to form an emulsion. From this activity, we can conclude that the presence of soap in water makes the oil mix with water. Let us prepare soap using vegetable oil, caustic soda and common salt. Take about 20 ml of vegetable oil in a beaker. Add to it about 30 ml of caustic soda solution or sodium hydroxide solution. To this solution, now add about 5 to 10 grams of common salt. Now, heat the mixture with constant stirring till a paste of soap is formed. Common salt decreases the solubility of soap, because of which soap separates out from the solution. Stir the mixture well and allow it to cool. On cooling the solution, solid soap separates out. But there are a few limitations of using soap. Soap cannot be used for washing clothes in hard water. Hard water contains calcium and magnesium salts. When soap is mixed in hard water, most of the soap mixes with the calcium and magnesium ions of water to form an insoluble precipitate called scum. So a larger amount of soap is needed for washing clothes. This scum sticks to the clothes being washed, which makes the cleaning of the clothes difficult. This difficulty can be overcome if detergents are used in place of soaps. Detergents are sodium salts of long-chain benzene sulfonic acids or long-chain alkyl hydrogen sulfates. These do not form insoluble calcium or magnesium salts in hard water and hence can be used for washing clothes even in hard water. Let us perform some activities to understand the action of hard water and soft water on soaps and detergents. Take about 10 ml of soft water, that is distilled water, and about 10 ml of hard water, that is water obtained from a hand pump, in separate test tubes. Add about 5 drops of soap solution in both the test tubes. Cork both the test tubes and shake them vigorously. We see that a lot of lather is formed in the test tube containing distilled water and there is no lather formed in the test tube containing hard water. A white curd-like scum is formed in this test tube. From this activity, we can conclude that soap lathers easily in soft water and does not lather easily in hard water. In order to obtain more lather in hard water, more soap has to be added. Activity. Take about 10 ml of hard water in 2 separate test tubes. Add about 5 drops of soap solution to one test tube and about 5 drops of detergent solution in the other test tube. Cork both the test tubes and shake them vigorously. We see that no lather is formed in the test tube in which soap solution has been added. A white curd-like scum is also formed in the test tube. In the test tube containing detergent solution, a lot of lather is formed. This activity shows that soaps do not lather in hard water, while detergents lather in hard water. Would we be able to check whether a sample of water is hard by using detergents? Since detergents lather easily in soft water as well as hard water, hence we would not be able to check whether a sample of water is hard by using detergents. We use laundry soaps or detergents for washing clothes as they are better cleansing agents than bath soaps. Bath soaps use high-quality fats or oils as raw materials as compared to the fats and oils used in laundry soaps. We have also experienced that expensive and better quality perfumes are used in bath soaps as compared to those used in laundry soaps. Bath soaps do not harm the skin, as the manufacturing processes used in bath soaps ensure that there is no free alkali content present in them. Such care is not taken in the manufacturing processes used in laundry soaps. Hence, it has been observed that most laundry soaps are harmful for the skin.